Hello everyone, myself Saithaja from Triple E department. Subject is matrix and calculus. Today TikTok presentation about the eigenvalues are orthogonals. In this presentation we can see the eigenvalues are orthogonals or not. Let's see the presentation. Eigenvalues are orthogonal. Eigenvalues themselves are not orthogonals. Rather, it is the eigenvectors corresponding to distinct eigenvalues that can be orthogonals. When you find the eigenvalues and eigenvectors of a square matrix, the eigenvectors corresponding to different eigenvalues are guaranteed to be linearly independent. If the eigenvectors are also normalized, have a length of 1, then they can form an orthogonal set. This property is especially useful in diagonalization matrix. Here we can see orthogonals are not eigenvalues are not orthogonals. Eigenvalues. Eigenvalues are a special set of a scalar associated with a linear system of equation, that is a matrix equation, that are sometimes also known as characteristic roots. The determination of the eigenvalues and eigenvectors of a system is extremely important in physics and engineering, where it is equivalent to matrix diagonalization and raises in such common application as stability, analyzes the physics of rotating bodies and small association of vibrating system, to name only a few. Each eigenvalue is paired with a corresponding so-called eigenvectors, or in general a corresponding right eigenvectors and a corresponding left eigenvectors. There is no analogous distinctions between left and right for eigenvalues. The decomposition of a square matrix into eigenvalues and eigenvectors is known in this work as eigendecomposition, and the facts that this decomposition is always possible as long as the matrix consisting of these eigenvectors of a square is known as the eigendecomposition theorem. The algorithm in an algorithm for computing the eigenvalues and eigenvectors for large symmetric spare matrix. Here we can see the eigenvalue example. There are eigenvalues. There are scalar values that represent how two matrices stretch or compress space. They are not orthogonal to each other. Eigenvalues are the solution to characteristic equation that A minus lambda is equals to 0, where A is a square matrix, lambda is the eigenvalue, and I is the identity matrix. Here we can see the problem solving by the eigenvalue. Eigenvector. In linear algebra, it is often important to know which vector have their direction unchanged by a linear transformation. An eigenvector or characteristic vector is such a vector. A linear transformation rotates, stretches, or shears the vector it acts upon. Its eigenvectors are those vectors that are only stretched with no rotation or shear. And an eigenvector or characteristic equation is such a matrix is such a vector. In linear algebra, it is often important to know which vectors have their directions unchanged by a linear transformation. A linear transformation rotates, stretches, or shears the vectors it acts upon. Its eigenvectors are those vectors that are only stretched with no rotation or shears. The corresponding eigenvalues is the factors by which an eigenvector is stretched or squished. If the eigenvalues is negative, the eigenvector's direction is reversed. In this point we can see when the eigenvalues are negative integers, then the eigenvector's direction were reversed. The eigenvectors and eigenvalues of a transformation serves to characterize it, and so they play important role in all the areas where linear algebra is applied, from geology to quantum mechanism. There is a direct correspondence between n by n square matrix and linear transformation from an n-dimension vector space into itself. Give any basic of the vector space. We can see the eigenvector example. Eigenvectors. These are vectors associated with each eigenvalues. Eigenvectors corresponding to different eigenvalues are guaranteed to be linearly independent if they are also normalized and corresponding to distinct eigenvalues. They form an orthogonal set. Here we can see how we solve the eigenvectors. We can find two eigenvectors for quadratic equation, three eigenvectors for cubic equations. These are vectors associated with each eigenvalue. Eigenvectors corresponding to different eigenvalues are guaranteed to be linear independent if they are also normalized and corresponding to distinct eigenvalue. They form an orthogonal set. Orthogonality of eigenvectors. Orthogonality of properties. If V1, V2, V3, V4 up to Vn are eigenvectors of a real symmetric matrix, corresponding to distinct eigenvalue. Lambda 1, lambda 1, lambda 2 up to lambda n, then these eigenvectors are orthogonal to each other. Symmetric matrix. The orthogonality properties holds specially for real symmetric matrix. For non-symmetric matrix, eigenvectors corresponding to distinct eigenvalues may not be orthogonal. Normalization. Eigenvectors are often normalized to have a length of 1 to simplify calculation. Normalized eigenvectors are sometimes referred to as unit eigenvectors. Diagonalization. If a matrix A has n linearly dependent eigenvectors, it can be diagonalized as A is equal to PDP PD P inverse, where P is the matrix of eigenvectors and D is the diagonal matrix of the corresponding eigenvalues. Applications. Orthogonal eigenvectors are crucial in various applications, such as principal component analysis (PCA), where the eigenvectors form a new basis that captures the most significant variability in the data. Complex eigenvalues. While eigenvalues and eigenvectors can be real, they can also be complex. Complex eigenvalues often rises in the context of rotations and oscillations in system. Conclusion. The concept of eigenvalues and I are the fundamental components of linear algebra with broad application across derived fields. Eigenvalues represent the scaling factors in linear transformation, while eigenvectors point to the direction that remains unchanged or scaled during the transformation. Key points to LHC include orth- orthogonality. Eigenvectors corresponding to distinct eigenvalues of real symmetric matrix are orthogonal, forming a basic that simplifies various mathematical computation. Application. Eigenvalues and eigenvectors find application in diverse fields such as data analysis, quantum mechanism, control system, graphic theory, and numerical method. Geometrical interpretation. Interpretation. Eigenvalues and eigenvectors have a geometric interpretation, providing insight into the scaling and transformation behaviors of matrix. Complex eigenvalues. Eigenvalues and eigenvectors can be real or complex, allowing for a comprehensive understanding of transformation, including rotation and oscillation. Spectral theorem. For real symmetric matrix, eigenvectors can form an orthogonal basis, a concept utilized in various advanced mathematical and physical applications. Thank you.